Hello, welcome everybody to the 2025 Randall Research Scholars Live event. My name is Cole Seeley and I'm giving the first presentation. So I'm working in Dr. David Dixon's lab in his computational chemistry lab on a project titled Predicting Acid-Base Properties of Halomethanes. So in this project I'm using Gaussian and MolPro computational software to calculate the properties of halomethanes and comparing these to known experimental values and trends. So this work is in collaboration with Dr. Vittorio Pace at the University of Rome, and I also am working with Dalton Andrus, a grad student in Dr. Dixon's lab. So how does computational chemistry work? Essentially, it uses computing power to solve the Schrödinger equation, listed here in the middle, with the Hamiltonian at the top here. And this gives us energies for different chemical systems. In a very simplifying description, this involves the use of methods-based sets and approximations. One such approximation being the Born-Oppenheimer approximation, which assumes that the nuclei of atoms don't move at all in comparison to the movement of the electrons. So on the other hand, there's always a trade-off. So as you can see here, we balance system size against accuracy and cost. So as you use more accurate methods, they get more computationally costly and limit the amount of size that your system can be. So in this presentation, we use a method called G3MP2, which is a composite method and falls right around in these quantum mechanical methods up here. So why halomethanes? So a halomethane is a 5-atom molecule with tetrahedral geometry and carbon at the center. And the other 4 atoms are either halogens or hydrogens. So currently, halomethanes do not have their properties consistently experimentally published. However, this work would create a reliable, complete reference table for any chemist looking to use halomethanes in their work. And for this presentation specifically, we have examined the degradation pathways of these molecules, stripping one atom off all at a time, all the way down to the carbon. So for our previous work, we stripped the hydrogen off of the atom, off of the molecule, giving us pKa's of all the hydrogenated halomethanes. And we did this in multiple solutions, being H2O, DMSO, acetonitrile, and THF. So pKa, for those who don't know, is the willingness of a species to associate its hydrogen proton in solution. And so the lower the pKa, the more likely it is to donate the hydrogen. So these values were extremely sparse for the halomethane series. Only about 3 of them were present for the entire series. For some reference, ethanol would have a pKa value of around 16 and ethane would be around 50. So with our credibility from this previous work, these values are able to function as references for these chemists around the world, and also you'll see the values in the rest of the presentation are able to do that as well. So going on to our fragmentations. So the first fragmentation, as you can see with the reaction here at the bottom, you take the halomethane and you take one atom off, creating the halomethane radical. So in this graph, you can see each of the lines corresponds to a different atom being stripped off, and then it's a associated bond association energy. So you can see that there's a massive nonlinear drop in bond association energy, or the bonds getting weaker, as you go down the periodic table from fluorine to iodine. However, when you go from hydrogen to fluorine, it instead increases. You can also see that the fluorine bond association energy is about, on average, twice as much as the iodine bond association energy. And so although atomic mass doesn't map perfectly onto halogen substitution, you can see a general downward trend with a lower bond association energy with a higher halogen substitution. And if you're very keen, you can notice some groupings in the graph which correspond to similar substitutions of similar molecules, such as CF2Cl compared to CF2Br. So next, going on to the carbene and the carbynes, which are the carbon attached to 2 atoms and carbon attached to 1 atom, we validated our methods by comparing our calculated heats of formation to experimental heats of formation found in active thermochemical tables. And as you can see, our values in this first column here, compared to the second column, are very, very close. And they approach the standard of chemical accuracy, which is around 1 kilocalorie per mole, or just over 4 kilojoules per mole. The table here is in kilojoules per mole. And finally, all molecules shown here are in the ground state, and the splitting column on the right being the energy gap between the triplet and the singlet state for the carbenes, or the doublet and the quartet state for the carbynes, tells us about the stability of the molecule. For example, the positive value of 9.4 for CH2 corresponds to its unique tendency to be in a triplet ground state as opposed to the rest of the carbenes. So continuing our degradation pathway and taking that halomethane radical and dissociating it into the singlet or triplet carbene, these are wildly important molecules, these carbenes, because they have many medicinal, environmental, and industrial applications. And specifically here in this graph, we're looking at the adiabatic BDEs, which means that we're going straight from ground state to ground state. And you can see that the periodic trends from before stay consistent from the previous dissociation, and you're able to see more of these halogen trends in the substitution. So next we go into the carbynes, which are very important as they're very difficult to measure in experiments due to their nanosecond lifespans. And again, you can see those periodic trends are being consistent once again with the weaker bonds as you go further down the periodic table. And then just to point out some values, our strongest here would be the F bond dissociation energy for the molecule CHF, and our weakest would be this 226 value here for the iodine bond dissociation energy of CFI. So finally, putting together everything, we've mapped the sequential dissociation pathways for each of the parent molecules, for lack of a better term, CH4 to CH3 to CH2 to CH and C. And this gives us an interesting perspective on, as you can see, how the methane tends to a near downward trend, whereas the other halogenated species, besides tetrafluoromethane, tend upward. And you can also notice that there's this very unique drop in bond dissociation energy with the tetrafluoromethane pathway. So in summary, we have produced the most complete set of pKa values for the hydrogenated halomethanes across aqueous and organic solvents. We have confirmed consistent periodic trends where bond dissociation energies decrease, moving significantly down the periodic table. And we have achieved excellent agreement with the experimental heats of formation verifying high accuracy predictive capabilities. And for future work, we want to further examine that tetrafluoromethane pathway, as well as the redox reactions of these molecules, taking into account their charged counterparts. Here are our citations along with the previous paper. And thank you. Do you have any questions?
I think it's on slide 4 you motivated or mentioned that there was a scarcity of information about these pKa values. So I don't know, I'm not sure I understood why though. So is this because it's such a complex problem, or is it taking the computational issues, or why was there not a large data set already in place?
I'm not entirely sure, but I believe it is because some of these, like I said, are very difficult to deal with experimentally. So for example, those carbynes, those nanosecond lifespans are very difficult. So some of these molecules are extremely hard to deal with, especially because when we're talking in the gas phase, they can be hard to measure.
Looking at slide 10, why do you think there is that big drop in the BDE for the CF4 pathway?
My personal theory is that the CF2 carbene is very stable, and that's what contributes to this big drop in energy. And you can actually see, going back to the splitting, that it has, it very much prefers that singlet state. So that's my theory. However, we're going to look into that more.
Kind of naive in the area, but back to the nanosecond kind of lifespan, how do you actually would measure that? Are you doing that in a simulation, or are you actually doing the real measurement? And if so, what kind of instrumentation or what kind of processes allow you to do that?
I personally am not familiar with how they measure the lifespans of these molecules, as I work in the computational side of things. So that would be definitely a question for the experimental chemist.
I'll answer that. They don't have nanoseconds. They have infinite lifetimes if they're in ultra-high vacuum. They don't fall apart. They have those kind of lifetimes if they're in air where there's oxygen, but in a vacuum system, they're around forever.
Thank you.
did you choose G3MP2 as your method?
So we actually use multiple methods in this project. G3MP2 is just featured in this presentation. We use G3MP2, B3-LIP, along with the FPD method, or the Feller-Peterson-Dixon method, which is an extremely accurate but also very costly method. It's also composite, and with our upcoming manuscript of the data, most of the values will be in FPD, and you'll be able to see the most accurate, up-to-date set of all of these properties.
I'm just curious, basic level, how do chemists publish these data sets? Is it just simply put on a website and here it is, or is there a more organized, formal way where the community knows and kind of like archives these things?
I'm not sure of the standardization.
Go to your last slide.
Sorry?
Go to your last slide. No, one back. Right under the codes, that's the answer.
Oh, well, yes. So an example is the active thermochemical tables. So that's one of the places where we source our data, and chemists also source their data for all of their reference values when they're looking.
Go to your second reference there. What's that?
The Gaussian computational
No,
cell.
the third reference then. Sorry.
That's our previous paper for which we calculated our properties for the pKa's. So.